The main purpose of this skill is to generalize the ability to solve the differential equation for a transmission line system with either an inductor or a capacitor on a generator or the load side. So you want to be able to solve for all four combinations, and let's do that by working through two generic cases. Let's look at the situation where there's an inductor on the generator side and a capacitor on the load side. So I've broken this down into steps, and we'll keep everything symbolic. That way, when you solve through the process, you'll be able to apply it to other problems that are similar. To start, let's outline our two problems that we'll just kind of solve in parallel, step by step. So the first is the capacitor on the load side. So we have a generator with an impedance. We'll just say it's not impedance matched for now. And this is our input voltage. Take it into a transmission line with characteristic impedance Z0. And then you have a capacitor at the termination. And so the side of the transmission line with the reactive load in question, we'll call the voltage, we'll call the junction. So this will be the voltage at the junction, and we'll have the current coming out, current at the junction. In this case, VJ is what we've been referring to as V out. Separately, we'll also solve the situation where we have the same generator and with its impedance, and we have an inductor before we go into the transmission line. So in this case, the reactive load is on the generator side, and we'll keep this as an open circuit. Characteristic impedance Z0. And in this case, our VJ will be referring to Vin. So IJ in this case goes into the transmission line. VJ is what we've been traditionally referring to as Vin. So there's a number of steps. I probably won't be able to do it all in this board, so try to follow along, but I'll try to keep as much of it on this screen as possible. The first step is to draw the Thevenin equivalent of the junction in question, the junction with the reactive load, and you want to more specifically relate the voltage at the junction and the current at the junction to what I'll call the frowny face. So going to past examples, I've been referring to the frowny face as whatever V plus or V minus is going out of the transmission line. And when I have a smiley face, that's into the line, because it's fun inside the transmission line, so we'll say they're happy going in and sad coming out. So what I mean specifically is that in the case of this, we're on the load side. So V frowny face is referring to coming out of the line, so that would be V plus. Conversely, when I say V frowny face here, it's the direction coming out, so V frowny face would be what we've been referring to as V minus, the negative going wave. But either way, draw the Thevenin equivalent, and so that we can relate the outgoing wave to VJ and IJ. So let's start by doing that here. We have 2V plus source, and with an impedance, that's the characteristic impedance of the transmission line. And then this is our voltage at the junction. This is our capacitor, and our current in the junction is defined as this direction. Let's do that for the inductor case. There's a lot more going on here. So on the transmission side, we have a source that's 2 times the negative going wave. Again, the direction of the wave that's coming out, with a source impedance that's equal to Z0, the characteristic impedance of the transmission line. In this case, it's connected to the inductor, the generator impedance, and then finally VG. So there's a lot more going on here. And then in this case, we're calling Vj as the potential between here. And one thing to note is that Ij is now is defined as the current going into the transmission line, because this is a generator end. So to write out the equation, this relation, we also want to use the fact that the current is going to be C dV dt, and the voltage across the inductor is going to be L di dt. So using that and looking at the circuit, let's do that for this capacitor circuit here. So we'll have 2V plus is equal to the voltage drop, Z0 times the current. So Z0, and the current is C dV dt, plus the voltage at the junction. So now we've related Vj, this is dVj, or Ij in this case, but we just went ahead and substituted it, and then 2V plus over here on this side. Now let's do that on the inductor circuit. There's more components here, but we have Vg. This potential here is going to be equal to all the voltage drops across this loop, right? So we're going to do Kirchhoff's voltage law across this entire circuit. So Vg is going to be equal to the voltage drop across Zg. So we have Ij Zg plus the potential drop across the inductor, which is L dij dt. And then we also have the voltage drop across Z0, so Ij Z0 plus 2V minus. In the case of the inductor, one thing to keep in mind is that this is Vj. So another expression for Vj is going to be Ij Z0 plus 2V minus. This is something to keep in mind because we might come back and use it later at the very end. Just as a preview, the reason we might use this at the very end is, in this case, we're solving for voltage, which is what we're commonly asking for. In this case, you solve for the current when you solve the differential equation, and to convert that to voltage, you might use this relationship over here. So the next step, we'll look at the two scenarios separately, but for the capacitor or the inductor load circuit, we want to move the Vj in the case of the capacitor, or the Ij terms to the left-hand side of the equation. So that would give us, so the ultimate goal is to get a first order differential equation. So doing that, let's move some things around. So in this case, the first order differential equation is dVj over dt is going to be equal plus 1 over Z0 C. So we divide that over. We divide everything by Z0 C so that the coefficient for dVj dt is equal to 1. Vj is going to be equal to 2V plus all over Z0 C. And then similarly, if we do the same thing on this side, we want to normalize everything to di dt, so we're going to divide everything by L and move some things around. So we're going to have dij dt plus, in this case there's two ij terms, so we have Cg plus Z naught, all divided by L, so we're going to divide everything by L, so that the dij dt term has a coefficient of 1. And on the other side, we have all the voltages. So we have Vg minus 2V minus all over L. So this is the differential equation that we're going to solve for the capacitor case. This is the differential equation that we're going to solve for the inductor case. Now the next step is to solve for the homogeneous and the particular solution. So so I'm going to do some cleanup here. I'm going to remove all the step 1 stuff. We don't necessarily need the Thevenin equivalent circuit to stare at anymore. And I'll just rewrite the full differential equation up here so that we can have that to stare at. So for the capacitor circuit, we have dVj dt plus 1 over Z naught C. Vj is going to be equal to 2V plus over Z naught C. And then for the inductor, we have d by dt ij plus Cg plus Z naught all over L of ij is going to be equal to Vg minus 2V minus over L. And with that, I'll erase what's on the bottom. Now you may recall that the general process to solve a differential equation is you have to first solve for the homogeneous solution, which is where the differential equation, the right-hand side is equal to 0 for the homogeneous solution. And then you solve for what we call the particular solution, where we let this equal to what we see, so 2V plus over Z naught C for the particular solution. So that is going to be our next step. So the homogeneous solution gives you something that will always give you 0 going in, which is kind of the source-free solution. So if there isn't a voltage at the source, then the homogeneous solution would be your overall solution, and the particular solution would just be 0. And then if there is a source, in this case there's a voltage source going on, you have an equation that when you run it through this will produce this right-hand side as the output. So let's start by looking at the homogeneous solution, and that is what our step 3 is. So step 3 is find the homogeneous solution. And one thing I'll note is that we should also time shift as needed. Now, if you already know Laplace transforms, there's a straightforward way to solve this in the general first order differential equation that's quite elegant. Or you may remember there's also a little trick where you set Vj to be equal to uv, and then you do some manipulation of the differentiation of dVj dt and a lot of acrobatics. But the other way that we can use for the time being when we first learned differential equations was just the guess and check approach. So for the homogeneous solution, we want to set this right hand side equal to 0, and we can see that the solution will be of this form. It's going to be an exponential e to the minus t over the time constant tau, but then also time shifted by capital T, because it takes time t to cross to the other side. Since this is on the load side, you have to time shift by capital T. And then at the same time, it's 0 before that, so we want to multiply it by a step function, u of t minus t. So that's going to be our homogeneous equation. If you substitute this into the differential equation, you'll see that you get 0 if tau is equal to RC, so Z naught C. And this will be valid from T going from capital T to right before capital 3T. The reason it's not valid after that is if there's a mismatch here at 3T, you're going to have another reflection come over, and then this equation by itself isn't valid anymore. For the current, it's the same form of differential equation. Again, we're setting the right-hand side equal to 0, and the solution will take the form IJ. The homogeneous solution is going to be equal to A e to the minus t over tau, and it's 0 before that, so we'll multiply it by the step function. And in this case, there's no time shift because we're on the generator side, so there's no propagation. And there's no propagation that we need to worry about. Now, at the same time, this is not valid for all time if there are reflections, so this is only valid from 0 to 2t. Because at 2t, the ingoing wave would have made a round trip. It's an open circuit here, so all of it will bounce back, and we're going to have to... So basically, it's valid until the next reflection comes in to mess things up for you. Next up, we want to find the particular solution. So find the particular solution. And when we do that, we'll see that if we put in just a first order equation, so VJP is going to be E plus FT, that you can plug this in and have that equal to a constant. Similarly, for the inductor situation, you can have Ij of P is equal to E plus Ft. Now, one thing to keep in mind is that since this circuit doesn't blow up as t goes to infinity, we can observe that since Vj of p t goes to infinity is not infinity, it doesn't blow up, and therefore the f is always going to be equal to 0. So that leaves us the E that we have to solve for. So now we're going to combine this to find the solution. So you combine it, and you're going to use the boundary conditions to solve for the constants. In this case, we are going to solve for the values at t is equal to the initial condition where stuff starts happening. So in this case, we're going to have something for t equals to capital T. In this case, we have the initial condition of what the situation is like for t equals to 0. And the other boundary condition we have for both of these cases is as t goes to infinity, or as the capacitor and inductor charge. And using those boundary conditions, we can then solve for the constants A and E. But first things first, let's combine these terms to get the solution. So Vj is going to be equal to these two added together. So we're going to have A e to the minus t minus capital T over tau plus E u of t minus capital T. And then in this case, Ij is going to be equal to A e to the minus t over tau plus E u of t. Let's start with the t goes to infinity boundary condition. Because that one's a little bit easier to solve if we do that one first. So as t goes to infinity, we see in this circuit the transmission line goes away, the capacitor turns into an open circuit, And so the voltage will simply be the generator voltage. So Vj is going to be equal to Vg. As t goes to infinity, this exponential term goes away. So what that means is that E is going to be equal to Vg. The other boundary condition we have is that at t is equal to, in this case, 0 is capital T, because that's when stuff starts happening. So when t is equal to capital T, this is 0. So when t is equal to capital T, Vj is going to be equal to 0, because this is behaving like a short. So if we plug that in, you will find that when t is equal to big T, this exponential is equal to 1. So a plus e has to equal to 0, which means that a is going to be equal to minus Vg. And so plugging that in, we get our final solution for the junction, for the voltage, which is Vg. We can factor out the Vg. 1 minus e to the minus t minus big T over tau, close parentheses, u of t minus capital T. So that is our final answer for this capacitor load. And we did it. So now let's do that to this inductor load. Let's start out by taking the t goes to infinity boundary condition. Now the general assumption that takes place is we assume that the transmission line is infinitely long for the purposes of solving this differential equation, so that when the inductor becomes a short, you're still staring at the mouth of the tunnel. So you're still looking at Zg and Z0. If in that situation, the current that's going into the transmission line is going to be equal to Vg over Zg plus Z0. So going back to the mouth of the tunnel analogy, Vg is going to see this Zg and Z0 in series, and so the total amount of current is going to be Vg divided by the sum of the two impedances. And so what that means is as t goes infinity, this term goes away, so that is what E is going to be equal to. Similarly, when t is going to be equal to 0, when t first turns on, this inductor looks like an open, and so Ij is going to be equal to 0. And so in order for that to happen, that means that A is going to be equal to negative E, which is going to be equal to minus Vg over Zg plus Z0. So putting all that together, we can then get our solution for Ij, which is going to be equal to Vg, Zg plus Z0. We're going to factor that out, just like we did with the voltage expression. 1 minus e to the minus t over tau, u of t. And that is our solution for this circuit. Now remember, one other note, I'm just going to clear off some room up top so I can write a little something. We can talk about this circuit just a little bit more. Suppose we want to find out what the voltage is instead of the current. Well, we'll go back to that one thing I pointed out a little bit more towards the beginning of the video when we looked at the Thevenin equivalent circuit. Remember that the voltage at the junction is going to be equal to Ij times Z0, and then the equivalent voltage source here is going to be equal to 2V minus. Now at t equals 0, there's no reflected wave yet, and so we can assume that V minus is equal to 0. And so if what you wanted was the voltage instead of the current, going in for that initial time period, you just multiply the result by Z0. So in this case, the voltage at the junction is going to be equal to VG Z0 over ZG plus Z0, and then 1 minus e to the minus t over tau u of t. So now we also have the voltage. Once we have these two things solved, you might have to do a little bit of cleverness and some tricks to solve for other quantities. So you might want to find the voltage after propagating through the transmission line once you know what's going in. And so if you want to propagate by t, propagate to the other side, then you just have to time shift by t, capital T. Or another thing that you might want to do is to find the reflection. So you might need to use the fact that Vj is going to be equal to 1 plus gamma V. We'll just say it's equal to 1 plus gamma, the voltage coming out. And so you can, and using the fact that the voltage that's going in, the reflected voltage, is going to be equal to gamma V frowny face, you can also use that to figure out what the wave going in the other direction is. Another trick that might happen is this might be a change in situation, so you might need to connect it to something that was happening before, in which case your boundary condition situation would be different. So you would say that at t equals a particular time, maybe it has to be continuous with the value of what was going on before. So then you would plug in that time and solve for the constants so that they match up. So there might be little tricks that you have to do beginning from step 5 and onwards to find some other quantity. But in general, this is the process. It's the same process, just looks a little bit different depending on whether your reactive load is on the generator side or the load side. But if you follow the general procedure, you should be able to end up at the right equations and battle your way towards a solution.